Now we are going to see one of the most famous CNN, the network that outperformed classical methods on some image recognition tasks. This network is called AlexNet and was created in 2012. AlexNet uses the next ingredients: a ReLU activation function, a local response normalization, overlapping pooling, that is pooling with non-disjoint receptive fields, dropout, and data augmentation. The shape of the network is described here. You have on the left the input data and on the right the output layer. In between, there are several convolutional pooling layers and at the end, several dense layers. As noticed by the authors of this paper, CNN with ReLU activation functions can be trained several times faster than the same network using hyperbolic tangent function. On this plot, the training error is displayed. It decreases much faster when ReLU is used in the network, plain line, compared to the hyperbolic tangent function, the dotted line. This may be related to the fact that ReLU derivative is equal to 1 when it activates, which is much larger than for the hyperbolic tangent. Therefore, the optimization procedure can converge faster. We are now going to detail the local response normalization or brightness renormalization. So first, let AIXY be the activity of a pixel XY in the ith feature map followed by a ReLU function, and BIXY is the renormalized activity given by this formula. You can see that this quantity involves a sum over J, where J is a feature map index. Basically, here, the normalization is done by dividing the activation at a given position x, y in a feature map I by the sum of the activations at pixel x, y in the adjacent feature maps. This corresponds to a competition between the adjacent feature maps. They cannot all output large values for a given position x, y, since these values are normalized. The general idea is then to enforce diversity between feature maps. Note that the ordering of feature maps is arbitrary and determined before training. You can also look at this reference from 2009, which proposes a similar normalization procedure where the mean activity is subtracted. This procedure is called local contrast normalization. The overall architecture of AlexNet is as follows. The key point is that this architecture is split across two different GPUs, which most of the time do not communicate with each other. In this picture, you have one GPU at the top and one GPU at the bottom. They only communicate at some specific locations. For example, you have the input image, then you have one convolutional layer, then you have a second convolutional layer, and you see that between the first and the second convolutional layer, you have no connections between the GPU on the top and the GPU on the bottom. The second convolutional layer is going to use only the feature maps of the first convolutional layer that are stored in the same GPU. So it means that you have really two different streams in these architectures. At some point, these streams are put together. For example, between the second and the third convolutional layer, you have connections between the GPUs. Dividing the feature maps between two different GPUs is done mostly for computational reasons and to reduce the number of trainable parameters in the network. Besides, ReLU are applied after all convolutional layers and fully connected layers. The local response normalization is applied after ReLU in the first and second convolutional layer, and max pooling is applied after the first, second, and fifth convolutional layers.